Welcome folks to lecture lab 4, and in lab 4 we are interested in validating nodal and mesh analysis techniques. So basically you want to validate the nodal analysis technique and the mesh analysis technique in the lab. Let's move to the lab objectives. So the lab objectives of this lab are as follows. The first objective is that the students need to understand the definitions of nodal voltage and mesh current. Then the students need to validate nodal analysis technique in the laboratory setting. And the students need to validate the mesh analysis technique in a laboratory setting. And finally, the students need to validate calculated solution using B-Spice simulation. Basically, you're going to apply calculated solution to the circuit. Then you're going to do B-Spice simulation. And of course, your B-Spice simulation should match your calculated values. And you do that before you come to the lab. Then you build the circuits in the lab and you take measurements, and those measurements should be basically consistent with your calculated solution and B-Spice simulation. But before we start with the circuit, we need to brush on a few definitions. The first one we are looking at is what's the nodal voltage. The nodal voltage is defined as the voltage from that node, a given node, to the reference node. The reference node is a node in the circuit where the voltage is basically assumed to be zero. In real-world circuits, this is the ground node. We're going to call it the reference node. It's basically the zero voltage. So let's look at this circuit. This is the circuit similar to the one you're going to build in the lab. Maybe the values will change, maybe the value of the power supplies will change, but the circuit is going to look very much similar to this one. Now, if you look into the circuit, there is basically a total of 5 nodes. The most important node is the node at the bottom here. This node at the bottom is basically what we call the ground node. It has this symbol. The symbol means that this node is physically connected to ground. In the laboratory, the power supply will have a ground node. We need to make sure that the reference node is connected to ground. We do that for safety reasons. So this is the first node, which is the ground node, but there is also 4 more nodes. So let's look at this node over here, which is the node connected from the power supply to the resistor. Remember that the definition of a node is basically a point at which 2 or more elements are connected. So at this particular node, what we have is we have this power supply is connected to this resistor. So this is a node, and the voltage at this node is defined as the voltage from this node to the reference node. So the voltage from here to here is the same as the voltage of the power supply. I would expect the voltage here to be 10 volts because it is the voltage from this node to the reference node. That is basically going to be 10 volts. So we know the voltage at this node because there is a voltage source connected from this node to ground. This is a known node. We know the voltage at this node. It's basically equal to 10 volts. There is another node over here also where we have the 15 volts voltage source is connected to R5, the 5th resistor. So at this point we have a node, and the voltage at this node is also known, will equal to 15 volts because by definition the voltage at this node is basically the voltage from this node to ground. The voltage from this node to ground is the same as the voltage source. There is 2 more nodes. There is this node over here where we have 3 resistors are connected. We call it V1, and the voltage at this node is the voltage from this node to ground, which is the same as the voltage across R2. So the voltage across R2 is the same as V1. It's the voltage from this node to ground. There is another node, which is basically the node over here. We call it V2. Similar to V1, it's basically the voltage from this node to ground, which is the voltage across R4. The voltage across R4 is V2. So now we are interested in defining how we can use Ohm's law using nodal voltages. How to use Ohm's law using nodal voltages. So I'm going to come to this resistor, for example, and I'm going to use Ohm's law to define this current. I would say that what's the current over here going to equal to using Ohm's law. If I know the voltage across this resistor, R3, then I will be able to define the current very easily. But the voltage across R3, this voltage over here, gonna be basically minus V1 plus this voltage plus V2 equals 0. I'm applying KVL here. So the voltage across this resistor gonna be V1 minus V2. So the voltage from the left to the right gonna be V1 minus V2. And we do that by KVL. Now we can define the current very easily. So basically the current here gonna be, I'm gonna call it Ix, which will be V1 minus V2 over R3. V1 minus V2 over R3. If I say that what's the current in the opposite direction, it's gonna be basically V2 minus V1 over R3. So I can call it Iy. Iy will equal to V2 minus V1 over R3. Of course, this comes from KVL and Ohm's law. If the current goes this way, going to the left as an Iy, then the plus polarity going to be on the right, the minus polarity going to be on the left. This is by Ohm's law. However, if I say that current I'm using is Ix, then the plus polarity going to be over here on the left, and the minus polarity will be on the right. So now let's show you how we can do the nodal analysis technique. Basically, we're gonna sum the currents using KCL at the unknown nodes. So I need to sum the currents at V1 and I need to sum the currents at V2. So we sum the currents at each unknown nodes. We have here only V1 and V2 are unknown nodes. I know the voltage here is 10. I know the voltage here is 15. So the way we do it, the way we like to do it, is basically we're gonna sum all the currents leaving the node, leaving V1. So at V1, I'm gonna sum all the currents leaving the node. So I will apply KCL at V1. So if I write the equation when all the currents leaving the node, that's what I will have. I will have this current over here, which will be V1 minus 10 over R1. So I have V1 minus 10 over R1, which is the current leaving here. The current leaving R2 gonna be V1 minus 0 over R2, or basically V1 over R2. So I'm gonna say plus the second current, which is V1 minus 0 over R2, plus the third current, which is V1 minus V3 over R3. V1 minus V2 over R3. This will equal 0, because by KCL, if all the currents leaving the node, then the sum of all the currents leaving the node equals 0. I like summing the currents leaving the node equals 0 because it makes it more systematic. Now we're going to come to the second nodal equation, which is at V2. Again, we're going to say that all the currents leaving this node equals 0. Then at the second node, when we apply KCL, we're going to say that the first current going to be this one. So we're going to say that V2 minus V1 over R3. The current going to the left is V2 minus V1 over R3, which is minus the current going to the right. Here the current leaves V2, so it's going to be V2 minus V1 over R3. That's why we have it like this, right? Then the current leaving R5, which is V2 minus 15 over R3. And finally, the current leaving R4, which is V2 minus 0 over R4. So I add them all up, and this should equal to 0. What we will end up with here is two equations, two unknowns. The only unknowns we have in the circuit are going to be V1 and V2. And in the circuit, you have two nodal equations, and we will solve for the system of equations. What's important here is that you apply KCL at V1. You sum the currents at V1, and you apply KCL at V2. You sum the currents at V2 to solve for the voltages V1 and V2. So we apply KCL to solve for V1 and V2. In this lab, you're going to have a circuit. You're going to analyze the circuit. You're going to have the values for the nodes. Once you know the values for the nodal voltages, you can find the currents in any branch. So you can solve for the entire circuit. Once you solve for the currents and the voltages, you can solve for the power of each element also if you want it. Once you solve for the circuit, you need to simulate the circuit using BSpice. The value of your circuit simulation should match your calculated values. Then you're going to come to the lab, and when you come to the lab, you're going to build the circuit and you're going to measure it. So you're going to measure the voltage at this node, you're going to measure the voltage from V1 to ground, and this should match the value you have in your simulation and in your calculation. Also, you're going to measure the voltage across V2, at V2, which is the voltage from V2 to ground, and it's going to match also your calculated values. When it comes to measuring the currents, if you wanted to measure, for example, the current going through R1 in this direction, going to the right, you can break this resistor from this side, place the DMM in series between the R1 and the circuit, such that the current will enter the plus polarity of the DMM. Same thing with this resistor. You're going to break it from the top and you put the DMM in series between the circuit and the resistor. Here you break the resistor from the circuit and you place the DMM in series between the resistor and the circuit, and so forth. So I would expect you to know how to measure the currents and the voltages at this point, because we've been learning how to use the DMM from lab 1. So at this point you should be very proficient in measuring the voltages and the currents using the DMM. So the second part of this lab is basically that deals with mesh analysis. So the first thing we need to look at is the definition of the mesh current. The mesh current is basically the current that circulates within the mesh. So if you look into the circuit, for example, the circuit has 7 loops but 3 meshes. So meshes, usually the windows, they are loops that do not contain any loop in it. So this is the first loop, the first mesh, we're going to call it I1. This is the second mesh, we're going to call it I2, and this is the third mesh, we're going to give it a name I3. But there is more loops. For example, you can combine those 2 meshes to give you one loop, that's loop number 4. You can combine those 2 meshes like that. That will give you loop number 5. You can combine those 2 meshes so you can get something like that. This is going to be loop number 6. And you have the whole loop on the outside perimeter that combine the 3 meshes. So this is going to be loop number 7. So we have 3 meshes, which are the windows, the loops that do not contain any loop in them. And you have 4 more loops that are not meshes. So the mesh current is the current that circulates within the mesh. So if you look into, for example, mesh number 1, this is the current that circulates within this mesh. For mesh number 2, this is the current that circulates within mesh 2. And we're going to have a current that circulates within mesh 3, which is I3. My convention is to use the direction of the mesh current to be in the clockwise, same direction as the clock. It's a convention, you don't have to use it. I follow this because it is systematic. Most problems in our textbook uses this convention, the clockwise, but some textbooks might mix between clockwise and counterclockwise. It's going to be the same thing, but it's going to be less systematic. Basically, you will use the same techniques to solve for the circuit problem. So the current that flows through the outside perimeter of the mesh is the mesh current. So for example, if we come to I2, we know that the current flows through R4 gonna be I2. And keep in mind that you see the arrow of the direction of the current the same as the mesh current, right? So the direction of the mesh current can be the same as the arrow of the circular mesh here. And it's the same current flowing on the outside perimeter. So this is I2. For I1, it's going to be the current going through this power source, because the power source is on the outside perimeter. Finally, the current for I3 going to be the current flowing through this power source over here, and it's going down because the arrow should be in the same direction as I3. Now, if there is an element, any element between any two meshes, like for example R1 is between mesh I1 and I2, then the current going through this resistor is basically the algebraic sum of the two meshes. Any element shared between two meshes, the current flowing through this element, through this resistor, is the algebraic sum of those two meshes. Basically, that's what we said. So if you have R2 over here is between I1 and I3, and we said that this current will go down, then it's going to be I1 minus I3. Because the current is going down, and you're going to basically sum algebraically those two mesh currents. However, the current going up going to be I3 minus I1, right? Because you're going to follow the direction of the mesh currents. So now we're going to talk about how we can use Ohm's law using the mesh currents. So let's look at this resistor, for example, R4. So over here, I can easily say that the voltage across this resistor gonna be I2 times R3. I can call this voltage to be Vx, for example. It's gonna be I2 times R4, right? It's the same direction as the current. The current goes from the left to the right. That means the plus polarity gonna be from the left to the right. Then the voltage across this resistor going to be I2 times R4. Now let's say that you have the voltage across this resistor R1, and this resistor R1 is shared by those two meshes, and I have the plus polarity over here on the right and the negative polarity is on the left. That means, according to Ohm's law, the current will enter from the right to the left. That means it's going to be I2 minus I1. Then this voltage, I can call this voltage Vy. It's going to be I2 minus I1 times R1. V equal I times R, right? So the current going through this resistor is I2 minus I1. Now let's say that I wanted to find the voltage across the same resistor but on the opposite direction. The plus polarity is on the left and the minus polarity is on the right. Then I will use I1 minus I2 as a convention of the current. The current going to the right through R1 going to be I1 minus I2. So then we can call Vz, for example, to be I1 minus I2 times R1. Now keep in mind that those two voltages can have the same magnitude and opposite signs, which is clear here that Vy will equal to I2 minus I1 times R1, while Vz can equal to I1 minus I2 times R1. So that does make sense. So now what we are interested in is how would we apply the mesh analysis technique. Basically, we're gonna sum the voltages around each mesh and set it equal to 0. And then we're gonna use the plus polarity, the convention of the voltage drop, to be caused by the mesh current. So if I'm writing the equation for mesh number 1, I'm gonna sum the voltages around mesh number 1 equals 0. That's by KVL. And then I would use the voltage drop across the resistors to be caused by I1. So I would have the plus polarity here and the plus polarity here. So the mesh analysis technique basically states that we're gonna sum the voltages around each unknown meshes equal 0, and we're gonna set it equal to 0. This basically by KVL. That's how we do it, by KVL. So if I'm gonna come to mesh 1, for example, I'm gonna sum the voltages around this mesh equals 0. So when I sum the voltages around mesh number 1, I'm gonna have a convention. I know that when I sum the voltages around the mesh gonna equal 0. If I enter the minus polarity, I'm gonna subtract. If I enter the plus polarity, I'm gonna add. This is my convention, which is most textbooks conventions also. And then we're gonna assume that the voltage drop across the resistors is caused by I1, the same mesh current. So this is the equation, and let's show you how we did it. I will start with the voltage source because it's on the far left, and I'm gonna go clockwise. So I'm entering the minus polarity as I go clockwise. So I'm going to say minus this voltage, which is minus 10. And then I'm going to move to the next resistor. Next resistor will have a voltage drop caused by I1. The current through this resistor then going to be I1 minus I2. And to get the voltage, you multiply it by R1. So I have I1 minus I2 times R1. Then I'm going to add the voltage drop across this resistor. Again, the voltage drop is caused by I1. That means the plus polarity is on the top. So I will have I1 minus I3 times R2. This will equal 0. So this is the first mesh equation. Now I'm going to go to the second mesh equation, which is over here. So I'm going to sum the voltages around this mesh equals 0, but now I will use I2 as a reference that causes the voltage drop. So I will have basically this equation, and now the voltage drop across R4 is caused by I2. So I will have plus I2 times R4. Then the voltage drop across R3 is caused by I2. So I will have plus I2 minus I3 times R3. So that's what I have. I2 minus I3 times R3 plus the voltage across this resistor, which is I2 minus I1 times R1. And that will equal 0. Now keep in mind that when I sum the voltages around here, I used I2 as a reference, while when I sum the voltages around here, I used I1 as a reference. So it's clearly in the first mesh, I will have I1 minus I2, while on this mesh, I will have I2 minus I1 times R1. That's what I have here. So I1 minus I2 times R1 over here, and over here I will have I2 minus I1 times R1. This is the second equation that I have for the second mesh. Now I'm going to move to the third mesh. So at mesh number 3, we're going to apply KVL. So this is the equation we will have, where we will start with this resistor over here. Now the plus polarity is caused by I3, so it's at the bottom. Then we're going to say that I3 minus I1 times R2, which is what I have here. Then I will have this polarity over here caused by I3, so it's going to be I3 minus I2 times R3. And then this voltage here is going to be plus 15 equals 0. Because we have 3 unknown meshes, we're going to have 3 equations, 3 unknowns. You solve for the system of equations, and basically now you solve for the mesh currents. Once you solve for the mesh currents, you can solve for any voltage or any current in the circuit. So in this lab, you're going to solve for the circuit analytically, basically using your calculators. And then you're going to simulate the circuit using BSpice. You're going to validate that your BSpice simulation matches your calculation before you come to the lab. When you come to the lab, you're going to build the circuit and take measurements, and those measurements should match your calculated values and your simulated values. And now you know that you can use both techniques, because we know that it does work to solve for circuit problems. I hope you enjoyed this video, and I hope it's helpful to you, and thank you so much.